So what is differential thrust? Differential thrust is essentially when you have two propellers instead of one, and they're separated by a certain distance. When you control the yaw of the aircraft, instead of being controlled purely by standard control surfaces, such as the rudder, it is controlled by the difference in thrust created by these two propellers, in which when you turn, say, left, the outermost propeller will rotate faster than the innermost propeller, and it'll create a left turning motion. This aircraft also has drop tanks below the aircraft body. These drop tanks are controlled by an actuator, and the proposal is that during mid-flight, say during a turn or even a straightaway, the plane will be able to drop this payload and be able to land safely, all while being controlled with differential thrust. In the past, differential thrust in history, it has shown to be inherently unstable. We're trying to prove that with an inherently stable aircraft design, differential thrust can be used with great success.
We chose a Clark Y airfoil for this plane because mainly it's easy to manufacture and it has the flat bottom that produces a generous amount of lift. Because of the flat plate, it is great to have a top-mounted wing, as you can see here, because the bottom of the wing lays flush with the top of the fuselage, and making it modular actually allows it to be easier to transport when we are moving the plane. It can be in two pieces, and when we are dealing with anything electronic, it's easier to access all the electronics through the wing box where the two pieces connect. Moving on to the tail, the airfoil that we chose to have for the horizontal stabilizer and the vertical stabilizer was a NACA 0012 airfoil, and that is because it produces no lift, so that when the plane is in cruise, it can stabilize the lift that is generated by the wing itself. And then the control surfaces themselves, the ailerons, elevators, and the rudder, they were calculated, and the dimensions for those were decided using established parameters that we found from hobbyist websites.
Starting with the wing, first we had to take the Clark Y airfoil and turn it into a rib. Essentially we took that rib and made several cutouts of it. Those ribs are mounted to two main support spars, one on top, one on bottom. That allows for more support with less weight. We also have an additional spar in the back, and the ribs we cut out are shorter at the flight control surfaces to have enough room for the flight control surfaces. The fuselage starts with the semi-monocoque design. We have a series of bulkheads that are connected by stringers that run along the length of the plane. That allows for more structural support, while allowing us to have that internal space and giving more room for any sort of electronics that need to go inside. Not a single part on this plane was original from the initial design we made on Fusion 360. Almost every single part's been reiterated and redesigned to accommodate for tolerance, size, weight. A good example of that is some of the initial ribs didn't have the holes cut in them. That was one thing we added to allow for more weight.
So originally we had a balsa wood fuselage, but we quickly realized during the manufacturing phase that that wasn't feasible. It was just way too light of a wood, and it cracked under very easy pressure, and we needed something stronger, especially since the fuselage is dealing with a lot of forces, and that's where it's taking the brunt of most of the force. So we switched to a light plywood. It's stronger, but it's not as heavy as regular plywood.
I developed a system for the RC plane where we have a battery that stores all the power for the plane during flight in the front, which is followed by the receiver behind it, which communicates with our transmitter to get the pilot inputs and then have them output onto the plane itself. And then the receiver controls all actions on the plane, starting with the servos, which control our control surfaces in the rear and the wing. And then from the receiver, it also connects to an ESC, which is mounted on the underside of our wing, which then communicates with our motors. And in our case, for the differential thrust, there's only one ESC, and it splits to both of the motors, and it uses I2C protocol to actually take the input from the rudder, and it will actually transmit to the throttle control on both of the motors, which allows for a differential thrust as it combines both inputs and scales it accordingly. And during the manufacturing design process, some of the issues that we came across were the weight of the plane. We're expecting around 8.25 pounds, which makes it hard for the batteries. as we needed a power curve that will allow for around 50% throttle input. So when we use differential thrust in the air, the motors can scale accordingly and proportional throughout any increase and decrease throttle inputs. Additionally, there was also the thought of cost, as electronics are the most expensive input to the project. I had to make sure that we didn't go over budget in our case so that we don't exceed costs. And then finally, wiring for the plane was a little difficult, as our design introduces a two-part system where we have the fuselage separated and then the wing. And then the motors being mounted on top of the wing. I had to make sure that there was a way to disconnect all the wiring for the servos and the motors, so when we take the wing off, it actually stands individually.
We knew from the beginning, when starting with the payload, that it was going to be comprised of 4 parts. The first being the actuator, then the part holding the payload up, a part guaranteeing the release of the payload, and the payloads themselves. Those went through many iterations, including a slide system, using fishing weights as our payloads, and even making payloads with adjustable mounting. So when we eventually settled on a design, it ended up being a fork design, which attached to the actuator, and when extended would pull the payloads up to a wall, which would then push them off the ends of the fork. When we were printing, our main considerations were weight and strength. And then on top of that, to ensure that our pieces would actually endure the loads that they were bearing with the payload weights, we also factored in the print orientation during its manufacturing to prevent any breakage along the layer lines. So with that, the payloads were 3D printed because of the fact that they were made of more complex geometries than we would feasibly be able to manufacture out of wood or anything else. So they were printed out of PLA on my Bamboo X1C, and we are pretty confident with those considerations that this will hold up.
How's that? Good?
If we had installed the payload,
Alright, cool.
the actuator backwards.
So right now we just took off the
20% might be too much.
You want I can throw it down to 10.
Yeah.
We're here at Tangerine Field. Our last benchmark test was not a success, and we'll talk about why. Let's get into the plane. Let's get into the changes we've made. So the reason why the last plane didn't work was because our landing gear back here was not fixed to the rudder or to the fuselage at all. It was kind of acting as a shopping cart, didn't work at all. The front of the landing gear was way too narrow, way too light, and it was made out of steel wire. We replaced that with aluminum sheet. This is way more stable. It has a wider tractor. The plane won't topple over. We removed about 1/2 pound from the rear of the plane just from cutting wood alone. This used to be all fuselage. We've cut it short. We've trimmed some of the stringers. It's still strong. And for the wing, so as you can see, the inclination angle is actually a lot better, about 2 degrees up, and the flat plate is sitting right on the body of the plane. With all this, the plane should fly today.
As you should. Dude, I was gonna paint my nails, and then the day I wanted to paint them, this happens at the shop.
For us too, like a ton of it.
This is awesome.
Thank you.
Wow. This is
very
actually
good construction.
This is impressive. Wow. Who designed this? Who built it?
All of us, all 6 of us.
Group effort.
Group effort.
Wow. All 6 of y'all killed it.
Thank you, thank you. We'll pass on the word. Not all of us could make it today.
Oh, that is so wild.
It's
So
got
you
way more
guys,
power
you
than
guys
this.
designed the wood and everything. I mean, this was all 100% your idea. This is awesome.
Thank you.
Where's the center of gravity? Checked it. It's pretty good.
On the main spar.
As long as you tweak it
I couldn't ask for better. It's
Sorry.
it's got squishy tires too. It has squishy tires.
Guys,
Oh yeah.
really cool job.
Have you guys seen the movie Top Gun? Like that.
I'm so frightened right now. Oh my god. Oh my god.
Oh!
Oh my god.
It's gone.
Where did
Dude,
it go?
I can't find it.
Where did it go?
You see it?
Oh my god! Like Holy mother. That's half power.
Cooper, that's our baby! Oh my god! That's our baby.
Go. Holy oh my god. Oh god. Bro.
Where'd it go?
I don't know. I don't know what happened. No. What happened?
Cooper!
Justin!
Patrick's gonna cry.
I don't want to see.
Something happened and it rolled over to the side. Momentarily got it back, and then it went back into a spin, and I didn't have control.
We're gonna basically replace this piece of wood here, and we want the ribs. We'll glue the ribs back in. We're gonna fix this here and recover it. And this side took a really good impact. It held up.